Hello everyone, welcome to this first lecture on waves. So this is your syllabus. We are going to talk about the introduction, transverse and longitudinal waves. So these are the two topics that we are going to discuss in today's class. Then consecutively we will talk about displacement relation in a progressive wave, the speed of a traveling wave, the principle of superposition of waves, reflection of waves, beats and Doppler effect. So they will be discussed in subsequent classes. All right. So let us start our discussion on wave. So what is meant by wave? Wave is basically a disturbance which propagates in a medium. So in previous chapter we have talked about oscillation, where we have already discussed how a particle oscillates from its mean position to and fro both the side. Say for example, there is a simple pendulum which is oscillating along right and left from mean position. Waves are something that goes through a medium and sets the particle of the medium vibrating in simple harmonic motion. So this chapter is highly related with the previous chapter, that is simple harmonic motion or oscillations, right? So the formal definition of a wave goes like this. Wave motion is a disturbance that travels through the medium and is due to repeated periodic motion of particles of the medium. So it is the particles of the medium which is oscillating from its mean position, and the disturbance which is causing the particle to move in simple harmonic motion, that disturbance propagates in a particular direction. All right, so things will become more clear. For the time being, you just concentrate on this definition. The pictorial representation will come in next few slides. All right, so there are three basic types of waves. This is a very important thing because many times in my career, whenever I have asked people that what are the types of wave, uh, many at times or often people get confused what to answer. But there are three basic types of waves. One is the elastic or the mechanical wave. Second one is the electromagnetic waves. Or third one is the matter wave. So what is an elastic wave or mechanical wave? The waves which require a material medium. Now this is important. The requirement of material medium. All right. So the waves which require a material medium for their propagation are known as the mechanical waves. The medium must possess the property of elasticity and inertia. It can be further classified as transverse wave and longitudinal wave. All right. So you can cut this or you can write it as and, because both are two possible cases. By the way, this classification is based on the mode of propagation. Means if I ask how exactly the mechanical wave is propagating in a particular medium. So the mode of propagation can be either as a transverse or longitudinal. All right. So for example, water waves, you have got sound waves, the seismic waves. Seismic waves means the wave that we get whenever there is an earthquake. So these are the type of waves which require a material medium to propagate, and those are the class, they fall in the broader class of mechanical waves. All right. Next important thing is electromagnetic wave. So basically in this particular chapter we will be concentrating on mechanical waves only. However, it is important for you to know the other types of waves also. So the second type of wave is electromagnetic wave. So these are the waves which do not essentially require any material medium. However, material medium can be there. All right. So there is a slight difference, and you have to, concentrate at this particular point really, that these are the waves which can propagate even without a material medium. That means it doesn't require any material medium. But if a material medium is there, in that case also it can pass through that. Of course, depending on the scenario. So for example, what are the types? Types are visible light, the X-rays, the gamma rays, etc. That means the whole of electromagnetic spectrum. If you search electromagnetic spectrum in internet, you will get a whole lot of spectra, such as it starts with high frequency gamma ray, then goes down to X-rays, then ultraviolet, the visible rays. That means the VIBGYOR range: violet, indigo, green, uh, yellow, orange, red, etc. Then you have got infrared, then you have got microwaves and radio waves. So this complete spectrum of waves, they are known as electromagnetic wave. There is a reason why we call it electromagnetic wave, because they propagate by the oscillating electric and magnetic field. So maybe at this time you do not know what is an electric field, but that will eventually become clear in the next year, that means HS second year. So basically for the time being you just understand that these kinds of waves, they propagate by oscillating electric and magnetic field. All right, so in the pictorial representation this will become even more clear. There is third category of wave which is known as matter waves. Now these are little bit abstract in its construction and understanding, because these are basically the waves that are associated with material particles such as electrons, protons, and other fundamental particles. And even it could be associated with atoms and molecules. So they arise in quantum mechanical description of nature and are conceptually more abstract than the mechanical or electromagnetic waves. It is not exactly like mechanical or electromagnetic waves, which we can detect, rather, I can say, uh, to propagate in a particular direction. Matter waves are conceptually a little bit abstract. Abstract in the sense, in quantum mechanics, there is a hypothesis which is called de Broglie's hypothesis. Uh, the hypothesis says that every material particle in this world possesses dual nature. That means a particle nature and a wave nature. So every material particle can essentially be represented by either as a particle or as a wave. So that particular wave is known as matter wave. All right. So for this time being, I mean, in this particular chapter, these two classes of waves are not important at all for you to understand in a deep sense. Uh, but this first type, that means elastic or mechanical wave, is something that we are going to talk about really. All right. So we'll be talking about a disturbance which is propagating in a medium, and that disturbance set the particles of the medium into vibration. They vibrate simple harmonically. That means from a mean position, they go either up or down or right or left based upon what is the mode of transport of the mechanical energy through that medium. All right. So here is a pictorial representation. Say for example, as we have already talked about, that water wave is a mechanical wave. So what we can see, if there is a drop of water gradually falling from top to the water surface, it sets the surface of the water into vibratory motion, and it is as if the stretched surface of the water is oscillating up and down. The particles of water, they oscillate up and down in this case, so giving rise to a wavy structure which is known as the mechanical wave. All right, so these waves, they propagate from one point to another into this water medium. But remember one thing, that the particles of the medium never gets along, never gets shifted along with the wave. That means if there is a particle at this point, the particle may either vibrate up and down, or it may go in this way longitudinally, but this particle will not go to another location. That means the medium will not shift, or the particles of the medium will not shift from one point to another. Just the wave energy will go from one part to another part of the medium. All right, this is a very important aspect of the propagation of mechanical wave. The particles of the medium through which the wave is going not at all gets displaced from one location to another location. All right, along with the wave. That's what I'm talking about. uh, but they may vibrate remaining in the same position. That means if there is a particle right here, it may either go to this point, return back, go to this point, return back. This is one set of vibration. Or if there is a particle here, this may go up, come down, down, and come up. So either it can go in a vertical oscillation, or it can go in a horizontal oscillation. What I'm saying is that this particle will not be transferred from this location to a new location. All right. So this will not go along with the wave. It will just remain in its position and vibrate over there. All right. Then this is a electromagnetic field. So as I said, this is electromagnetic wave, and electric and magnetic fields are oscillating perpendicular to each other. If the electric field is oscillating in this particular direction, magnetic field will oscillate in a different direction, and this is the direction in which the wave is propagating. So you will come to know more about this in the next year. And matter waves are very hard to detect in the sense we never detect it possibly. There is very sophisticated instrument should be designed in order to detect the matter waves. There are experiments by, say, G.P. Thomson and Davison and Garmer, who first detected matter waves due to electrons. And we essentially do not represent it pictorially, like we can capture down a picture of mechanical wave or electromagnetic wave, but for matter wave we sometimes represent it by this type of figures. All right. Many a times you will come across internet and with this picture. This essentially represents the matter wave due to, say, electrons in these cases. All right. So I'll not go in detail of discussion of matter waves. This will come whenever we will talk about quantum mechanics in a much detail. All right. So for the time being, you just understand mechanical wave. All right. Now, the propagation of mechanical wave, as I already have said, there are two different ways of propagation. So this classification is based upon the mode of propagation. Remember that, mode of propagation. So if the question is how mechanical waves can be classified based upon the mode of propagation, then you will answer it in this way. There are two modes of propagation of a mechanical wave. One is a transverse mode, and second one is a longitudinal mode. All right. So what is a transverse? Transverse, as the name suggests, that in this case the particles of the medium, they vibrate in a direction at right angles to the direction of propagation of wave. So that means if the wave is propagating in this particular direction, the particles of the medium either go up, then come down to the mean position. Suppose this is the mean position, y equal to 0, then again go down and again come up. So the particles of the medium will vibrate like this. All right. But the wave will propagate in this particular direction. It is quite like the water wave that you have seen just. That water molecules or water atoms, they just vibrate up and down, remaining in its own position. But the wave propagates from left to right, say. This is left, this is right. But the particles of the medium, they are propagating in a perpendicular direction to the direction of motion. All right. The wave is propagating in this direction. Particles are vibrating at right angle. This angle is actually 90 degree. This is the plan of vibration of the particle, and this is the direction of motion of the wave. So this angle is 90 degree. Hence, it is said that the particles of the medium is vibrating in a direction at right angles to the direction of propagation of the wave. If such is the scenario, then that type of propagation is known as transverse wave, or those waves in which case the propagation mode of propagation of which is like this are known as the transverse waves. So the portion of the wave that gets raised up during the wave propagation is known as the crest. The portion that gets depressed is known as the trough. So if this is the wave representation, then the portion of the wave which gets on top, this is known as the crest, and this is known as the trough. All right. Then there is something called longitudinal wave, which is quite opposite to this type of waves, which that is transverse waves. In transverse wave, we have seen the particles of the medium vibrate at right angles to the direction of motion of the wave. In the longitudinal wave, the particles of the medium vibrate along the direction of the motion of the wave. Suppose the wave is going in this particular direction, then the particles of the medium will also vibrate in this particular plan. So the plan of vibration of the particle and the direction of motion of the uh, wave remains the same. Now, for this type of propagation, some portion of the medium is compressed and some part is rarefied. So these type of waves there, that is why, but they propagate by successive compression and rarefaction of the medium. So this particular thing will become more clear. Already I have a GIF picture, so where it will become more clear, because pictorially things become clear even more. Just let us see this particular picture. What we can see in this case, this is a transverse mode of vibration. See, there is a disturbance propagating through these particles, and the particles of the medium, you can see, you can locate any particle. Suppose this particle, this is going just up or down. There is no other motion. It is not going horizontally. This motion is not there. It is either going up or coming down. So consecutively, what we can represent? We can represent these waves to be like this. That y, the displacement of the particle. What is y here? Y is the displacement of the particles of the medium. All right, so that is the reason why the oscillation chapter comes before wave, because in oscillation we have already known what is meant by oscillation, how exactly a particle may vibrate from its mean position to and fro. So in this case, what is happening? We are studying wave, but see, the particles of the medium through which the waves are propagating, those particles are being oscillated in a vertical direction. All right, so these are the particles of the medium, and they are oscillating to and fro in a vertical direction. So in that case, how exactly the displacement of those particles, any individual particle you consider, any individual particle, that displacement may be represented as a sinusoidal graph. So in that case, these portion, already as I have said, those portions which are on top, they are termed as crest. So this is one crest, this is also a crest. Doesn't matter if this wave may be propagated more, even if you extend it even more, then this is also a crest. And these regions are known as trough. So this is a trough, this is also a trough. All right. And this distance from one crest to one crest is known as the wavelength lambda, or from one trough to another trough is also the wavelength lambda, or from one point at this case to this particular point, this is also a wavelength lambda. So wavelength means what? Wavelength means the distance in which the particle completes one complete oscillation. In that case, or the distance required for the particle to complete one oscillation is known as the wavelength. So in this case, wherever the twice pi radian is completed of the oscillation, because you know, in one complete oscillation there are twice pi radian, and already we have known that the phase here is 0, this is pi by 2, this is pi, this is twice pi by 2, and this is twice pi. So wherever there is a twice pi distance covering, that is lambda, that distance is lambda. So lambda may be discussed, or lambda may be described in a way as this to this distance, or crest to crest distance, or trough to trough distance. I hope this part is clear. So this is a transverse wave that is getting propagated through a medium, and transverse wave is a part of mechanical wave based upon the mode of propagation of the wave in a medium. All right. So there is second mode of propagation, which is known as longitudinal. So let's talk about that. In this case, longitudinal wave means the particle of the medium, they vibrate along the direction of propagation of the wave. So in this case, you see the disturbance of the medium. So this is the wave. So this arrow is representing the wave. So this is the direction in which the wave is being propagated. But if you look at this particle, see this red dot where particle arrow mark is given, this particle is not getting from this location to any other location in the wave. It is just oscillating about a mean position. Suppose this is a mean position, then it is just oscillating like this in a horizontal plane. All right. And like this, not only this particle, this particle, this particle, this particle, or this particle, these are the particle, few particle markers uh, just represented so that you can understand. They are just seen to vibrate to and fro in the horizontal direction. All right. And in doing so, what you can see, there are certain zones of compression and rarefaction. See, because of this vibration, right, uh, see this particular portion, I cannot just stop it, otherwise I would have just shown you. I mean, this picture gives a clear cut understanding. You will see some zones where particles are clustered. This zone is known as the compressed zone. Compressed zone. And this zone where the particle density is little light, that is known as the rarefied zone. Right. So that is why longitudinal wave, they propagate by creating zones of compression and rarefaction. So if there is a compressed zone, the near neighbor zone will be a rarefied zone. Again there will be a compressed zone. Again there will be a rarefied zone. And again followed by a compressed zone, rarefied zone, like that. You can see that this whole animation in this particular figure. Alright. So sound waves basically is a longitudinal wave. So whenever we talk, we create sound wave. The sound wave propagates in a medium by creating these kind of zones of compression and rarefaction, and hence sound wave propagates through a medium longitudinally. That means it sets the particles of the medium to vibrate along the direction of the motion of the wave. All right, so clearly what we have understood till now, there are two classes of mechanical waves. One is transverse wave, one is longitudinal wave. The transverse wave is a type of wave where the particles of the medium vibrate in a direction perpendicular to the direction of motion of the wave. Longitudinal waves are the waves in which the particles of the medium oscillate in a direction of propagation of the wave. All right. So similarly, P wave, the primary wave of an earthquake, is an example of longitudinal waves. In earthquake, normally there are primaries and the secondaries kinds of waves. So primary wave out of that is a longitudinal wave. All right. Any kind of acoustic wave. Acoustic means something that goes forward by creating zones of high pressure or low pressure, because wherever there is a compression, that is a zone of high pressure. Wherever there is a rarefaction, that is a zone of low pressure. So we say that the decreasing pressure zone this is, and this is increasing pressure zone. So because there is a variation of pressure in the medium by which the wave propagates from one point to another, so that is why these are these fall under the broad class of acoustic waves. All right. So the waves which propagate, and because of whose propagation there is a pressure difference created in the medium, that's known as the acoustic waves. All right. Water waves. Uh, Basically, we knew till date that water wave is a transverse wave. That means particles of the medium, that is water molecules, they vibrate up and down, and the wave propagate in a direction horizontally. So for example, we can clearly see this particular crest that is moving in a horizontal direction, but recent simulation results that showed that actually the particles of the medium or a single water molecule, that doesn't essentially vibrate up and down or horizontally completely. It rather, see, it goes in a circle. So that means it has got both the components, both perpendicular component and horizontal component. So water waves is actually a mixture of both transverse and longitudinal vibrations. It is neither fully transverse nor fully longitudinal. Okay, so this particular simulation shows that. All right. So here it is written that water waves are the examples of wave that involve a combination of both longitudinal and transverse motion. As a wave travels through the water, the particles travel in a clockwise circle. The radius of the circle decreases as depth into the water increases. More the depth of water, the radius of the circle decreases. Of course it will decrease because the wave motion occurs mainly through the surface. As you go deeper and deeper into water, so for example deep down in ocean, hardly there will be a disturbance which is propagating through water. All right. So these are more surface waves, and in this case the water molecules, they rotate clockwise in a circle, and that is the reason why we have got both transverse and longitudinal patterns existing in water wave propagation. Clear? Now these are the characteristics of the wave motion. There are 7 characteristics. I don't intend to explain them individually. Rather, I suggest you to pause for a second or two and make a note from this particular slide. All right. So let us go back. Let us go forward to something new, that is differential equation of wave motion. So these are the two equations that you must remember, and not attempt to derive these two equations. Here what we have said, differential equation of wave motion is given as follows. By the way, so this y represents the displacement of the particle, and you can see it is second order in space, second order in time, and there is something called inverse velocity square. So v is the velocity of the wave. V is velocity of the wave. By the way, in wave chapter you will get two kinds of velocities. One is the velocity of the wave, second one is the velocity of the oscillating particle of the medium, and both are not the same. They are different things. So in this case, v that I am representing, that's the velocity of the wave, but y that I am representing, that essentially means the displacement of the particle, displacement of the particle of the medium. So it is in a sense that when a wave comes, that means a disturbance comes to a medium, and because of which to this disturbance the particles of the medium responds, and that is the reason why the particles are set into oscillation and the wave propagates in a particular direction. It's quite like as I'm talking, I'm creating or I'm imparting a pressure difference into the medium of air, and that because of that the particles of the air molecules or particles of the air medium, they simply keep on vibrating longitudinally. All right, so if you solve this particular thing, you remember this is a little complicated because this is a partial differential equation, not ordinary. In oscillation chapter, the differential equation that we got, that is an ordinary differential equation because that had only one independent variable, but in this case you have two independent variable. One is x, that is the spatial variable. Second one is t, that is the time variable. So in this case, this y, which is the displacement of the particle, it's a function of both position and time. So that is the reason why this is a partial differential equation whose solution is given by this: y is equal to a sine of k whole into x minus vt plus phi. So this k is known as the wave vector, phi is known as the phase angle or phase constant. It is quite similar to the conception of phase constant that we got in oscillation chapter. Okay, but anyway, we will talk about all these things individually. So terms associated with wave motion, as we had few terms associated with simple harmonic motion, so similarly there are terms associated with wave motion. The first term is amplitude. So this particular thing in this previous slide is known as the amplitude. So what it means? Amplitude is the maximum size of the disturbance, is known as the amplitude. So quite similar. Suppose this is the here it is given f. If I not write it as f, rather write it as y, in that case the particle of the medium to which it will vibrate or it will be displaced in a maximum. So this is y is equal to 0 limit. So the particle is set to oscillation, so it will go to one direction, reach a maximum, come down to mean position, and again go to another direction, reach a maximum. So this is known as the amplitude. So it is the maximum extent of vibration of the particle, or rather we can also say that the maximum size of the disturbance is known as the uh, particle. If you impart more energy to the system, the particle will get even more disturbed and they will vibrate even more violently. So the amplitude will also increase, right? Next, phase angle, that is phi, as already we have said, this is phase angle. So phase angle means the initial phase, means at time t equal to 0, what was the phase of the particle? That's known as phase angle, quite similar to the concept of that we got in simple harmonic motion. This is little new, wavefront. Why new? Because this conception, whole conception of wave actually started with the concept of wavefront. So wavefront means what? Suppose uh, there is a candle which is glowing. By the way, this is electromagnetic wave, but even in the case of uh, mechanical waves also, we can create some we can create some concepts of wavefronts. So for example, there is a disturbance in water medium. So this disturbance will propagate. So it will create circles around this point. So this is one wave. The next crest will suppose come here like that. So a wavefront is defined as the locus of all points which are in the same phase. So if this is the point of disturbance, something happens. Suppose you just have spotted or thrown a stone into the surface of the water, because of which the water wave started. So in that case, what will happen? The disturbance will propagate equally in every direction. It is not that the waves are getting created only in this direction. No, waves will get created in this direction also, in this direction also, this direction also. So what you can see that some circular patterns are just getting spread constantly with time. So these points which are in same phase means whose status is same at equal time, they are known as the wavefront. All right. So it's a little mathematical conception initially given by Christian Huygens, but remember that the whole concept or whole idea of wavefront actually whole idea of the chapter of wave started with the conception of wavefront. All right. So how exactly the shape of wavefront look like? So if there is a point source, there will be a spherical wavefront. By the way, sphere in the sense, why I'm talking about sphere, because I'm talking about 3 dimension. In 2 dimension, it will be a circle. All right. Line source. Say for example, you have got a tube light, that's a line source, but although tube light gives you electromagnetic wave, I am talking in this chapter for mechanical waves. There is a difference, but still, just for your understanding, if there is a line source, the wavefronts will be cylindrical. If there is a planar source, the wavefront will also be planar. Okay, very detailed analysis of this thing is not required. Just for your understanding, just small introduction I have tried to given in this particular slide. If any more detail is required, in that case you can let me know. I'll talk more about it. All right. Next, wavelength. Already we have talked about what is the meaning of wavelength, that whenever there is a one complete oscillation, the distance which is covered in one complete oscillation is known as the wavelength. So it could be the distance of crest to crest or trough to trough, or from this particular point to this particular point. This is also the wavelength. So 0 to twice pi radian, wherever it is covered, that's distance is known as one wavelength. All right. The differences are very clearly written in this slide. You can pause for a while and make your note. All right. So I always suggest that please make your own note while going through this lecture. Then time period. It is the time required for the wave for one complete oscillation. So the time required for one complete oscillation is known as time period. It is the time required to travel a distance of one wavelength. So in this time period, the wave travels one wavelength distance. All right. So the relation is given by lambda is equal to vt. V is the velocity of the wave, velocity of the wave, t is the time period. So if you know the velocity of the wave and time period, in that case, if you can multiply, you will get the wavelength. All right. Or you can get any other quantity. Suppose wavelength is given, time period is given, you can get the velocity of the wave. Frequency, the inverse of the time period is known as frequency, as we already we know in the from the oscillation chapter. And angular frequency omega, that is given by twice pi nu. All right. Or if you just place 1 by t over here, this will become twice pi by t, that is time period. Next, wave number. This is a little new concept and I'll talk a little detail about it in subsequent classes, not in this particular class. Just for today, remember that k is just twice pi by lambda. So wave number, sometimes we also call it to be wave vector, because this is a vector quantity. Twice pi by lambda is something that is known as wave number. As you know, omega, that is angular frequency, which is given by twice pi by t, that time period. Quite similar to this concept, k, the wave vector or wave number, is given by twice pi by lambda. Okay, this is something that you should remember. Then velocity of the wave. Now, what is meant by velocity of the wave? The velocity or the phase velocity of a wave, to be more precise, is defined as the velocity of its wave fronts. So what is the velocity with which the wavefront, you remember already, as I said, that if you have surface of a water, you make a disturbance, the disturbance will propagate gradually, making circular patterns which are known as the wavefront. So the velocity with which this wavefront propagate in forward direction, that itself is the velocity of the wave, or to be precise, we can call it to be phase velocity of the wave. All right, we'll also talk about this in more detail. So generally how we discuss it, or how do we define it? So let the wave front move a distance delta x in time delta t. In that case, velocity will be given by delta x by delta t. This is also given by omega by k. So this omega, this k, if you take the ratio, in that case you will get the v. There is a reason why you get v, because see, omega by k, from here we get twice pi by t whole into lambda divided by twice pi. So twice pi gets cancelled. You remain with lambda by t, and from the previous slide here, lambda by t is nothing but v. So if you place it over here, this is nothing but equal to velocity. So that is the reason why omega by k is equal to the velocity, or which is also, in other words, you can say to be v lambda. All right, nu lambda, sorry, this is nu. Nu is the frequency. Sometimes v is written as like this and nu is written like this. These two symbols, although look little identical, but there is a slight difference. You have to be a little cautious while following these slides. All right, so hopefully this is the last slide of this lecture. The phase means, phase is the position of a point in time, and that means at any instant or on a waveform cycle. A complete cycle is defined as the interval required for the waveform to return to its arbitrary initial value. So basically, as you know, phase, already talked in oscillation chapter, I told that phase gives you the instantaneous status of the particle. So in this case also, since the solution to the of the differential equation uh, gives the status of the particle, so phase essentially means at any instant of time where the particle of the medium is. So that's known as the phase, or in case of a wave, uh, uh, the instantaneous position is known as the phase. Phase difference means what? Suppose there are two waves which are little different. I mean, suppose these waves started with at the point y is equal to 0. This wave started with a 0 value, but this particular wave started with a different y value at time t equal to 0. Suppose this is time t, and this is the initial point. Since the initial point is different for these two different waves, there will be a difference in phase. All right, so this phase difference is known as theta. Essentially, this phase difference remains constant. uh, in general, it remains constant. Sometimes it may vary, of course, but in general, in this particular chapter, we will say that if there is a phase difference between two waves at initial time t equal to 0, that phase difference remains for all amount of time. So two oscillators means two sources which are giving out waves. Two oscillators that have the same frequency and no phase difference are said to be in phase. That means this is a situation, you see there is a red color, there is a blue color which are superimposed. That means one on top of the other. You really know no difference uh, in these cases. You cannot differentiate between the red and the blue color. They are just superimposing on each other. These kind of waves are known as in phase waves, or they are said to be in phase. If, on the other hand, two oscillators are there that have the same frequency and different phases, then we say that there is a phase difference and those two waves are said to be out of phase. That means, see here, these two waves now are out of phase. One started at time t equal to 0, started here, second one started here, and this difference is remaining everywhere. So there is a difference in phase between these two waves, and hence they are said to be out of phase. And if the phase difference is 180-degree, then they are said to be completely out of phase or anti-phase. So in this case, you see these waves started in a positive direction at time t equal to 0 after that, and this wave, both the waves had y equal to 0 at time t equal to 0, but as time increased, the first wave went in the positive y direction, second wave went in the negative y direction. So the phase difference between these two waves is 180-degree or pi radian. So if this is the case, that two waves have got 180-degree phase difference or 180-degree out of phase, then they are said to be in antiphase. All right. So this is a very brief description of the chapter wave. Please go through this chapter very carefully. And the next class, we will talk in more detail about the concept of wave number or wave vector and the speed of wave or the phase velocity of the wave. All right. So thank you so much.